Hey everyone, my name is Rick. I'm a fourth year studying math and physics at the University of Chicago, and today I'll be discussing my research on investigating the entanglement renormalization group flows of the so-called fractal spin liquids. And this was done under my mentor, Dr. Wilbur Shirley, in the Levin group. And you can see there's sort of an assortment of odd pictures that I'll get to each of them and explain why they're relevant here. But first, before I get started, I'd like to sort of mention, I think that people have developed a talent putting the word quantum in front of a lot of things. So we have like quantum cryptography, quantum internet, quantum money, and of course, quantum computers. But something that people don't talk about as often that I think is still super important is the concept of quantum hard drives or quantum memory. Because after we do these special calculations on the quantum computer, we want somewhere to store this like new novel information. And so to look at classical hard drives, the way these guys work is that classical information is just encoded in terms of zeros and ones, and the errors that you can have is that you can either have a zero flip to a one or vice versa. And what's very nice about classical hard drives is it's very hard for zero to flip into one and vice versa, because for a zero state to become a one state, all of those tiny little arrows, which represent these like magnets, all of them have to flip over, and for that to happen, it takes a lot of energy. So there's this energy barrier that makes it hard for these zeros and ones to flip into each other. But on the other hand, if we were to have a quantum hard drive, the basic unit of information would be these so-called quantum bits or qubits, where they are a linear combination of both like 0 and 1 at the same time. So you can do a lot more strange things with these so-called qubits. And unlike classical bits, there's two types of errors. There's the bit flip that you see with classical hard drives, but then there's also this so-called phase flip, where you can have like an additional minus sign that can be changed. And a couple years ago, researchers from Caltech proved that the most straightforward way to create a system with this like required energy barrier requires like 2 + 2, which is 4 spatial dimensions, which unfortunately we do not have access to. We don't live in a 4-dimensional world. That would be much more interesting. So the question is, what do we do? And instead of protecting these qubits, we can actually allow these qubits to interact with one another. So similar to how water molecules can interact with each other to give rise to emergent phenomena in the forms of like waves and vortices, if we arrange these qubits in a very specific way and define the way they interact with each other in a very particular way, then they can also give rise to emergent phenomena in the form of these quantum phases of matter. And the specific quantum phases of matter that we're interested in are these so-called topological phases of matter. And these are exotic because we can't describe them the same way we describe the well-known liquids and gases and solids. And what's nice about these phases of matter is that we can encode information sort of globally instead of locally, or topologically. We can encode the information topologically. And so we have these phases of matter that are very popular in the literature, and people are thinking about it because we can sort of use these phases of matter as like platforms for quantum computation. But this is not what my research was on. My research was on the so-called fracton phases of matter. And what's interesting about fracton phases of matter is that unlike these topological phases, so here I'll just quickly go over this example of topological order, you can sort of create like excitations or like disturbances within these qubits, and like these disturbances are like groups of particles. And these like groups of particles can like move freely along like a 2D lattice, and they act as if they were a single particle. So we call them quasiparticle excitations. Very, very strange. And they're called anyons, and you can sort of move them freely with each other and around each other by performing like physical operations in like a path on the lattice, on the 2-dimensional lattice of qubits. But these fracton phases, something very peculiar happens when we add one additional spatial dimension. So now we have like a 3-dimensional lattice, like a 3-dimensional grid with like these qubits on like the links of the grid. And these are much less understood. And the main difference between these phases of matter and topological phases of matter is that unlike topological, where the particles can like move freely, fracton phases of matter host these quasiparticle excitations that have constrained mobility. So some of them can't like move at all by the laws of the universe. You're just like stuck in place. It's very strange. Some of them can only move along a line, so they're called like lineons. And then some of them can only move along like planes, so they're called planons. And so a very paradigmatic example of these fracton phases of matter is called X-cube model, and this X-cube model hosts a variety of quasiparticle excitations that are either lineons, fractons, planons, and this like equation here on the left side you see like an H. The H stands for Hamiltonian, and that sort of dictates how the particles can interact with each other and what kind of energies they can have. The Hamiltonian describes the energies of the system, so it's very important. So that's the XQ model. The model that I'm more interested in are these family of fractal models called fractal spin liquids. And the reason why they're called fractal is because unlike with these topological phases where you just need to have lines or like loops or paths to move these quasiparticle excitations or produce them, for these fractal spin liquids you need to perform operations that form this very intricate fractal geometry. So if you look on the left-hand bottom corner, you can see that at the end, at the base and the top, you can see like a fractal geometry that's referred to as the Sierpinski triangle. It's one of the most famous fractals out there. And I'm interested in these fractal spin liquids and how they can be used for maybe potentially serving as a platform for quantum memory and quantum hard drives. And so how do we do that? I'm interested in what happens when we take one of these models and like we zoom out, and then so that means like every one of these like lattice spacings between the qubits get larger and larger. And the way we can sort of formalize this is that these like groups of qubits on the right side, all the little nodes represent qubits. We can group each block of qubits and then just like choose one representative spin qubit for each block. So when we do that, so like suppose I choose like this one, this one, this one, this one, this one, and these top left corners, then now the distance between the representative qubits are larger than just the distance between like the individual qubits. So it's like sort of coarse-graining the lattice, and that way it sort of represents you zooming out the system and seeing how the model changes. And specifically, I'm interested in how these entanglement properties, which are sort of non-local correlations that only exist in the quantum regime, they don't exist at all in the world that we live in, how that entanglement changes with these models. And so what happens is, for some of these models, there's a very specific transformation you can apply on the model. They're called local unitary transformations. When you do it, the model can split into two different or two same models. With the XQ model that you saw earlier, when you apply this transformation where you like choose a qubit from each individual block to make the lattice spacing larger, it turns out that you get back like the same model but with like larger lattice spacings, but then also a different model. So if you look at X cube, you have like the Hamiltonian for like X cube, XC, but then after you coarse grain, you end up with X cube and then toric code, which is TC. There are two different models. And on the other hand, with the fractal spin liquid or the Sierpinski prism model, when you coarse grain out, you end up with the two same models. And it's very strange. We don't fully understand why that's the case. And so when it splits into two different models, that's referred to as like AB bifurcation. When it splits into the same types of models, and that's referred to as self-bifurcation. And my project sort of the goal is to understand why this happens, and the way we went about doing this is, okay, can we like generate and like try to classify like families of these like fractal spin liquids? And my mentor and I worked on that sort of process, and that process is referred to as gauging. And essentially the idea is like we start off with a model that has like no quantumness, and we apply certain mathematical operations on it that involve like the symmetries of the model, and then you come out with like a fractal spin liquid. For instance, if you start with a model whose Hamiltonian has terms that look like a square, then after you gauge the model, you end up with the X cube model that we just saw earlier. But we can generalize this process. So you have a square here, and you can like sort of imagine a square for each like dot, so that can form like a four-tiled piece. But instead of 4 tiles, we can maybe take one out and we have like 3 pieces, or maybe add like a bunch of pieces. And those sort of tiles are called like polyominoes, and you see like tetrominoes in Tetris because all the pieces have like 4 pieces. And you can have like 6 pieces or 6 squares instead. And here's like the family of all sort of possible hexaominoes that are all distinct to each other, up to like rotations and shears and other sort of transformations you can apply on them. And sort of each piece can correspond to like a fractal spin liquid. And what's interesting is earlier we can see how we have this fractal geometry at the top and the bottom of these operators that are required to create these quasiparticle excitations. We can have like other more strange fractals that are generated from these pieces, such as these ones. And they look very strange, but you can almost imagine that these fractal geometries exist for the operators that are required to create these fracton excitations for these specific fractal spin liquids. So I generated a bunch of them, and my mentor and I sort of try to probe into the properties and the entanglement properties of these models. And sort of one thing that we did was look at how many different ways are there to sort of configure the qubits so that you have like just the lowest energy possible. That's sort of referred to as the ground state degeneracy. And so for models where it looks like there's self-bifurcation, so it like splits into two copies, you can see that clearly if you start with a model that's whose lattice spacing is 6, and you like sort of zoom out so you have 12 instead, what should happen is that you split into two copies, so you just double the ground state degeneracy. So you go from like, here you go from 10 to 20, when you double the lattice spacing from 6 to 12, so that's like self-bifurcation. On the other hand, you have like this AB bifurcation, or maybe it is AB bifurcation, we're not fully sure yet, but if we increase or double the lattice space by 2 from 6 to 12, then 7 doesn't go to 14, just goes to 15. So there's sort of this discrepancy that may correlate to AB bifurcation of these models, and that's like sort of one way that we were trying to probe these fractal spin liquids and see how the entanglement changes for these models when we coarse grain the lattice. And so the broad idea is instead of using energy barriers, we can take advantage of topological phases, which some of them are very special in the sense that they can have like quasiparticle excitations with constrained mobility, so those are fracton phases, and these fractons then have fractals, and so we can take advantage of these fractals to try to provide and create a platform for quantum hard drives. And characterizing these fractal spin liquids and their universal properties is like the key to realizing them in future quantum materials. Like these phases of matter actually don't exist yet, but we want to manifest them so that we can use them at some point. And hopefully we can do that. And yeah, thank you guys. Any questions?
I don't have any questions, but I do have a comment. You are an amazing presenter. Like, you kept everyone's attention the entire time. Some of the stuff I didn't quite understand, but I was really engaged, and it makes me want to kind of look into some of this now. But yes, you did an
I appreciate it.
amazing
Thank you so
job.
much.
Amazing.
Thank you so much. I appreciate that.